In this video, we'll talk about momentum theory for wind turbines. We will start with the traditional Betz theory and then extend it to include wake rotation. This video will contain the full derivations for both models. Let's start with an introduction. In wind power, we have a flow of kinetic energy from the wind. Now, assume that we have a cross-sectional area, here represented by our turbine. Define the incoming wind speed as V in. The kinetic energy is given by 1/2 times mass velocity squared. To calculate the power, we take the time derivative of the energy. Here, the variable that changes with time is the mass passing through the turbine. This is called the mass flow, the MDT, which we'll denote as m dot. Now, how large is the mass flow? Let the blue block represent the mass that will pass through the turbine. The size of this block can be represented by its area A and the length of it, which is given by the velocity and the time. We know that the mass is the density multiplied by the volume, where the volume is the area multiplied by the velocity and the time. This gives us that the mass flow is the mass divided by the time, which becomes the density multiplied by the area and the velocity. The available power now becomes 1/2 times the area and velocity cubed. Let's define the power of the turbine as the power of the wind multiplied by the power coefficient, which becomes. The power coefficient is a measure of how much of the energy in the wind that the turbine can absorb. Note that the power coefficient is not the same as the efficiency. Efficiency is related to how much of the incoming energy that is converted to heat. However, for the wind, some of the kinetic energy will be left behind the turbine, and the flow can pass outside the turbine as well. In both these cases, another turbine could utilize this remaining energy, hence the energy is not lost as heat. The power coefficient is therefore easier to work with, as it does not care if the energy that the turbine cannot absorb becomes heat, or if it just remains as kinetic energy. Let's also introduce the thrust force, which acts on the turbine in the same direction as the wind. The thrust force will also have a corresponding thrust coefficient. We will come back to these later in the Betz theory derivations. To derive the Betz theory, start by introducing a stream tube. The idea behind the stream tube is that we choose its size to ensure that there is no flow through the sides of the stream tube. The stream tube will have an inlet where the flow enters the stream tube and an outlet where the same flow leaves the stream tube. We now need some assumptions for the Betz theory derivation. First, we neglect all losses. For the flow, we will assume the following. No flow through the stream tube walls. This gives us 3 distinct flow velocities. First is the inlet velocity V in. We have the velocity at the turbine disk, which we call Vt. And finally, the outlet velocity, which we call V out. Constant flow speed over every cross-section, so that the flow at the turbine is the same for the entire turbine surface. Similarly, there's only one speed at the entire inlet and one at the entire outlet. Let's now introduce the area of the stream tube A in at the inlet, the turbine area A, and the outlet area A out. We assume undisturbed flow outside the stream tube. This is especially important for the outlet due to energy conservation, as we assume that we only decrease the flow velocity inside the stream tube. The implication here is that we can only absorb energy from the flow that actually passes through the turbine, while we don't change the energy of the flow outside the turbine, hence undisturbed flow velocity. We neglect turbulence, and we assume that the flow is stationary, which means that the time derivative is 0. We assume that the wake behind the turbine is infinitely long, so it does not decay. The flow direction does not change. This means that we assume that expansion of the stream to be so slow that we can neglect the radial velocity. Let's start the derivation. The first equation we're going to use is the continuity equation. We use this equation on integral form, which applies for control volume. First, define the control volume as the stream tube. We call the surface of the volume the control surface. Let's start by briefly explaining the terms of the equation. The volume integral, which is the density integrated over the volume, will be the mass in the control volume. This means that the time derivative makes this term represent the change of mass inside the control volume. The surface integral of the control surface represents the mass flow through the walls of the control volume. Here, the inlet and outlet. As we assume stationary flow, all time derivatives are zero, and we can neglect the first term. VCS is the motion of the control volume, but our control volume will be stationary, so this term becomes zero. Now, let's look at the inlet. The normal vector is always pointing outwards from the volume. The velocity is the incoming velocity. We see that the velocity and the normal vector have opposite directions, which will make the dot product negative for the inlet. We need to carry out the integral over the inlet area. As the flow is constant over each cross-section, we can just multiply by the area. And the inlet expression becomes minus density velocity in area in. Let's continue to the outlet. The velocity is V out. The normal vector is in the same direction as the flow velocity. This will make the dot product positive for the outlet. We integrate over A out here, and the expression becomes density velocity out area out. As the integral is a closed surface integral, we need to study the sides as well. But since we assume no flow through the sides, this part of the integral becomes zero, and the sides will not contribute. As the total integral is zero, we see that the expression density multiplied by the velocity and the area is the same for both inlet and outlet. Let's change control volume to only include the part up to the turbine. Remember that the continuity equation is true for all control volumes. Here we see that the control volume exit becomes the turbine. Therefore, the expression is similar for this cross-section as well, which is rho VTA. Remember that the density multiplied by the velocity and the area is the mass flow as we showed earlier. Let's save this equation. Now we will add assumptions about the turbine. Our first assumption is that the turbine is a flat disk without any thickness. This flat disk should be perpendicular to the flow as seen in the figure. The flat disk will cause a drop in the pressure. This drop is constant over the whole surface, just as the flow is constant over the surface. It is this drop in pressure that will extract energy from the flow. For the pressure, we'll assume the following. We have atmospheric pressure at the inlet. The pressure will return to atmospheric pressure at the outlet. We will also assume atmospheric pressure everywhere outside the stream tube. I will discuss this assumption a bit more later in the video. Let's continue to our next equation, the momentum equation. This is Newton's second law, rewritten for control volumes. Our first term is the external force on the fluid in the control volume. This can be pressure forces, shear forces, gravity, and external objects. However, gravity can be neglected for wind turbines, and since we neglect all losses, we will not have any shear forces, as those are associated to friction forces in the fluid. Therefore, we only need to care about pressure and the turbine. The volume integral represents the change of momentum in the control volume, and the surface integral represents the momentum flow through its walls. Let's start by analyzing the pressure forces. We see that the outside pressure is the same on the entire surface. Hence, the external pressure will not contribute to the force. Therefore, the only external force will be the thrust force of the turbine. We will add it with a minus sign, as the external force is force on the fluid, while the fluid's force on the turbine is in the opposite direction. Let's calculate the thrust force. It is given by the pressure in front of the turbine multiplied by the area, minus the pressure on the opposite side multiplied by the same area. Note that P1 is larger than the atmospheric pressure and P2 is smaller than it. We have a common factor A. Now match the minus sign and insert into the momentum equation. The flow is stationary, so we can remove the volume integral. The control volume is not moving. Now look at the inlet. Same as for the continuity equation, we will get the minus sign and can multiply the terms with area. The outlet will give a positive sign, otherwise the same expression. No flow through the side walls means no momentum flux through them either. Let us use the continuity equation to replace the area. We can also note from the continuity equation that the term ρ VA is the mass flow. The same can be applied for the outlet. Cancel the mass flow. Multiply by the velocity at the turbine. Reorder. The third equation we need is Bernoulli's equation. This equation is used to compare points in the flow domain. Compared to the previous two equations, which always are true, there are several conditions that must be met for Bernoulli to be valid. The first is inviscid flow. This is true since we neglect all losses. Incompressible flow. The flow can be approximated as incompressible for Mach numbers below 0.3. This means that if the wind speed is below 100 meters per second, we can perform our calculation as the air is incompressible. Stationary flow. This is one of our assumptions for the flow. Along a streamline or irrotational flow. As long as we compare 2 points inside the stream tube, this is fine. But we should be careful when comparing points inside the stream tube with points outside. The final condition, which normally isn't mentioned because it usually is true, is that the flow domain should be continuous. Here we have a discontinuity in pressure when we cross the turbine. Hence, we cannot use Bernoulli between the upwind and downwind parts of the stream tube. The third term in Bernoulli's equation is the term that depends on the height. This term is responsible for the buoyancy force. In air, we can typically neglect this term. The common form when we use Bernoulli's equation is to compare two different points. As we want to use Bernoulli to calculate the pressure, move all the terms except PA to the right hand side. Now we should choose points to compare. Place point A at the turbine on the upwind side and place point B at the inlet. PA is P1. VA is the velocity at the turbine. PB is the atmospheric pressure. VB is the inlet velocity. Write down the equation for these points. Now, use Bernoulli for the downwind part. Place point A at the turbine on the downwind side and place point B at the outlet. PA is now P2. VA is still the velocity at the turbine. PB is the atmospheric pressure. VB is the outlet velocity. Write down the equation for the downwind region. Now, we want to combine all the equations. Start from the momentum equation. Use Bernoulli downwind to replace P2. Use Bernoulli upwind to replace P1. Remove the parentheses. The atmospheric pressures cancel. The velocity at the turbine cancels as well. Note that this expression is still the difference between the pressures. Cancel the densities. Apply the conjugate rule to this term. Cancel the velocity difference. This is our first result. We have that the velocity at the turbine is the average between the velocity at the inlet and velocity at the outlet. Note that these two equations on the left are almost the same, except for the minus sign. Change the sign and save it. Multiply by 2 and solve for V out. For our next step, we are going to calculate the turbine power. This can be done by calculating the work performed by the turbine. The energy is the force multiplied by distance. Take the time derivative, which is the power. The time derivative acts on the distance, which becomes the velocity. As we are calculating the turbine power, the force should be the thrust force of the turbine, and the velocity should be the velocity at the turbine. Insert the expression for the thrust force, and use the expression for the pressure difference. Write 1/2 rho outside parentheses. Insert V out into the expression. Expand the square. Remove parentheses. Cancel the inlet velocity. Vt is a common factor. 4 as well. Introduce the axial induction factor A, which is a dimensionless value. It indicates how much the velocity slows down by the turbine. 0 means that the turbine does not affect the flow at all, and large values means that the flow slows down a lot. Replace the velocity at the turbine using the axial induction factor. Combine all inlet velocity terms. Remove parentheses and cancel the 1. Reorder. This is our expression for the turbine power expressed as a function of our axial induction factor. This is one of our important results from the derivation. Let us also set up the expression for the thrust force. We use that it is the power divided by the velocity. Use the definition of the axial induction factor. Insert the power. We can now cancel these. And have our expression for the thrust force as a function of our axial induction factor. This is another result of our momentum theory. Let's bring back the expression for the power coefficient. Note that these two are identical. That means that these two also have to be identical. And we have an expression for the power coefficient as a function of the axial induction factor. Let us bring back the expression for the thrust coefficient as well. In the same way as before, we can identify the expression for the thrust coefficient as a function of the axial induction factor. Before we continue, let's check the limits for the axial induction factor. Use the expression for the velocity at the turbine combined with the definition of the axial induction factor. Multiply by 2 and collect the V in terms. This is the expression for the outlet wind speed. We can see that if A is larger than 0.5, we would have negative wind speed at the outlet. In that case, we cannot have a stream tube as shown in the figure. Hence, the model becomes invalid. This gives the condition that A should be between 0 and 0.5 in this model. Values smaller than 0 would make the turbine into a fan. Values larger than 0.5 are possible, but we need another model to describe it. Now it's time to calculate the maximum power. Start by the expression for the power coefficient. Take the derivative with respect to A and find the zeros. We use the product rule for differentiation. For cancel. Expand parentheses with the 2. Expand the square. Collect the terms. This is a standard second order equation. We can write the roots. The roots are 1 over 3 and 1. Use that we know the interval for A, which gives us that the solution we want is 1 over 3. Which is the optimal axial induction factor. Insert in the power coefficient equation and we get 16 over 27, or approximately 59.3%. This is the famous Betz limit. It tells us that the highest power coefficient we can have for a turbine is 16 over 27, which would be the case for a perfect turbine without any losses. Let us also calculate the thrust coefficient for this case. We get that the optimal turbine should have a thrust coefficient of 8 over 9. Let's plot this result. First we have the power coefficient. We have plotted all the way to A equals 1 even though it is invalid above 0.5. This is to show that the model just predicts a decreasing power coefficient, which is what we would expect for a real turbine. Let's add in the optimal point. We can also plot the thrust coefficient. Note that this one peaks at A equals 0.5 and decreases in the invalid region. In reality, we would expect even larger thrust coefficients if we manage to get that large axial induction factors. This is due to momentum conservation, as we would have a larger change in flow velocity. We can also add in the line for the mass flow. This shows us that larger axial induction factors give lower mass flow through the turbine. This is the main reason why we are limited in how large power coefficients we can have. A large axial induction factor means that we extract a lot of the energy from the flow that passes through the turbine, but it decreases the mass flow, causing the flow to go around the turbine instead. Hence, we have to pick the best compromise for the axial induction factor, which is 1 over 3. Now I want to discuss the assumption used that we have atmospheric pressure outside the stream tube. This assumption can be questioned since the pressure should be continuous everywhere except through the turbine disk. Hence, one could think that this will cause problems outside the stream tube close to the turbine. However, this issue can be removed by expanding the stream tube. Outside the stream tube, we should have inlet velocity both at the inlet and at the outlet according to our assumptions. If the velocities are the same, there is no change in momentum. No change in momentum means no force. Hence, expanding the stream tube should not change the external force in any way. This means that expanded stream tube should give exactly the same results as before. Now we can make the claim that if we expand the stream tube enough, the pressure at the expanded stream tube should be atmospheric since it is far away from the turbine. Therefore, assuming atmospheric pressure on the stream tube will give correct results. Let us instead discuss the actual model limitations. First, for the real turbine, we have wind shear, which means that the wind speed varies with height, while we assume the constant speed. A real turbine will experience atmospheric turbulence. Turbulence will cause the wake to decay, so the assumption that the wake is infinitely long is not even close to reality. We always have losses, which reduces our performance. The turbine has a finite number of blades. We assumed an even pressure drop, while in reality it occurs at the blade positions. The way to approximate an even pressure drop would be with infinitely many blades that are infinitely thin. The turbine has a finite rotational speed. This leads us to the topic of wake rotation. So this is the end of the Betz theory derivation, and we will now continue and talk about the wake rotation for the remaining part of this video. Let us consider an axial turbine. In the Betz theory, we assume that the thrust force generates the power. But for the real turbine, the power is generated by the tangential force. The tangential force will cause the turbine to rotate. Let's call the rotational velocity omega. The power for a real turbine will now be given by the torque from the tangential force multiplied by the rotational speed. As the tangential force causes the turbine to rotate in one direction, Newton's law states that we must have a force on the fluid in the opposite direction. This will cause the flow to start rotating in the opposite direction. Call this rotation of the fluid small omega. A simple sketch of the rotation is seen here. The flow enters in a straight line, and when it passes the turbine, it starts to rotate. A rotating flow means that there is kinetic energy in the flow due to the rotation. If there is more kinetic energy after the turbine, we have absorbed less energy. Hence, wake rotation will reduce the maximum power that it can absorb. We have to assume that the wake rotation will depend on the radial position. Hence, we are going to create a radial segment and do all our calculations for this segment. At the end, we can integrate over all the segments to get the results for the turbine. Let's call the segment I, and for all variables that are unique for this segment, which are the variables that depend on the radius, we will put an index I to them. Define the radius of this segment Ri and call the width, which is small, dr. The area of the segment now becomes 2 pi Ri dr. Define the positive direction clockwise, which is the direction of the wake rotation. We will now add the tangential velocity Vti for this segment. The velocity will become a vector. Here we use cylindrical coordinates and call the directions radial, tangential and normal direction. We still assume that the flow in the radial direction is small and we neglect it. The normal direction is the direction we used for the Betz theory derivation. To stay consistent with Betz, we will therefore drop the index n here. Now convert the velocities into vectors. For the inlet this becomes, for the outlet it becomes. At the turbine it's more complicated. In the normal direction, we could assume that the velocity is the same on both sides. This comes directly from the continuity equation when we assume incompressible flow. But we are not violating any physical laws if we assume that flow velocity turns at the turbine disk, and therefore have different tangential velocities depending on which side of the turbine disk we are. Hence, use the tangential velocity Vt1 before the turbine disk and use the tangential velocity Vt2 after the turbine disk. we will also add a third tangential velocity inside the turbine disk. Now we are going to study the tangential velocity with the angular momentum equation. This equation relates the torque to the change in angular momentum. Here, Q is the external torque. As we have rotational symmetry, the pressure cannot give any contribution to the torque as it points to the center and thereby have a zero moment arm. The only external source for the torque is thereby the turbine torque. We can also note that torque is the tangential force multiplied by the radius. Similar to the momentum equation, we add it with the minus sign as Q is the torque on the turbine while the turbine applies torque on the fluid in the opposite direction. The tangential force mentioned here is the sum of the forces from all blades. As with all previous equations on integral form, the time-dependent term is 0. R will be the radius of our segment. V will be the tangential velocity. As the angle between them is 90 degrees, the cross product becomes a traditional multiplication between the two. We still have a stationary control volume, so this term is 0. Start by looking at the inlet, which as before will give a minus sign. Note that the term density and velocity multiplied by area is the mass flow. The expression for the outlet is similar but with a plus sign. Now move the control volume to end right before the turbine. As the turbine is outside the control volume, the external torque is 0. We replace the original outlet variables with the variables before the turbine. We assume that there is no wake rotation at the inlet, so Vt in is 0. One can now directly see that the tangential velocity before the turbine is 0 as well. Move the control volume to the other side of the turbine. The turbine is still outside the control volume, so the torque is still 0. The inlet now becomes the velocity directly after the turbine. We see that the angular momentum is equal after the turbine and at the outlet. We can cancel the mass flow. Let's bring back Bernoulli's equation as we used it in the Betz derivation. For the inlet, nothing has changed as the tangential velocity is 0. Behind the turbine, the expression has changed though, due to wake rotation. Use points A and B in the same way as before. PA is still P2. PB is also still the atmospheric pressure. VB will now have a tangential component. And VA also has a tangential component. This will create a coupling effect between the normal and tangential directions. We will now make the assumption that we can neglect this coupling effect. We will do it by neglecting wake expansion when doing angular momentum calculations. This is achieved by assuming that the outlet radius is equal to the turbine radius. Replace R out with Ri and cancel it. This gives that the tangential velocity at outlet is the same as at the turbine. Now, the tangential velocities in Bernoulli's equation will cancel and the pressure reduces to the same value as we had for the Betz theory. Let's go back to the full control volume with the turbine inside. We know that the tangential velocity at the inlet is 0, so this term can be removed. Replace the outlet radius with the turbine radius according to our approximation. We see that we have a jump in tangential velocity over the turbine. The remaining velocity is the velocity inside the turbine disk. If we only care about maximum power coefficient, we can ignore this one. But if we want to do calculations using the velocity at the turbine as input, we need to know its value. Hence, when we study the blade element momentum model, which is a topic for next video, we need this to calculate blade forces. To calculate the representative value, start by using energy conservation. One way to calculate power is the way we did in the Betz derivation and use that the power is the force multiplied by the velocity. The force is the thrust force in the normal direction and the tangential force in the tangential direction. The velocity is the velocity inside the turbine disk. The tangential force can be determined from the angular momentum equation. Cancel the radius and change the sign. Use the same thrust force as we had before. Insert the pressure difference. Perform the dot product. Reorder. Note that the term is the mass flow rate. A second way of calculating the power is to calculate the energy for the control volume. I have already simplified it a bit here and assumed that the only external term is the turbine power and that only the kinetic energy changes. We will use this equation to compare the incoming energy with the outgoing energy. The turbine is added with a minus sign as it removes energy from the flow. We still have stationary flow, so the time derivative is 0. VCS is still 0. Let's look at the inlet, which once again will give a minus sign from the dot product. The selected terms will become the mass flow rate. For the inlet, use the inlet velocity. For the outlet, use the outlet velocity and use that the dot product is positive. Change the sign. We have a common factor. Set the two expressions equal to each other. The V in and V out terms cancel. Cancel the mass flow rate and remove the minus sign. Divide by Vt. We can now see that the velocity inside the turbine disk is half the velocity after the turbine, which is similar to the normal velocity. But remember that the normal velocity has a smooth change in velocity, while the tangential velocity jumps at the turbine. Now, introduce the tip speed ratio lambda as r omega over V in. The radius is the full radius of the turbine. Omega is the rotational speed of the turbine. R omega will therefore be the movement speed of the blade. Hence, the tip speed ratio is the speed the blade is moving with divided by the inlet speed. So how many times faster than the incoming wind the blade is moving. This is an important design parameter for a turbine because a real turbine will have a tip speed ratio which gives optimal performance. The optimal value will be relatively independent on the incoming wind speed. We can also define a local tip speed ratio where we use the radius of our segment instead of the full turbine radius. There's a third way of calculating the power. That is mechanical power, which is the torque multiplied by the rotational speed. Here it is added with the minus sign as omega is in the negative direction. Replace the torque with the expression from the angular momentum equation. This power expression will have to be equal to the other two as well. Cancel the mass flow. Expand for the last term and move it to the other side. Multiply by r omega which will be a common factor. Introduce the angular induction factor A', which is similar to the actual induction factor but in the tangential direction. In other literature, it's common to define it from the wake rotation speed small omega. Hence, I will just show the expression here. Update the angular momentum equation with this factor. Replace Vt and combine the terms. Use the continuity equation to replace the mass flow. Use the actual induction factor to replace the velocity at the turbine. Reorder. We can also update the tangential velocity at the turbine. Replace Vt again and cancel the two. Now we are going to rewrite it in the rotating reference frame, which is the velocity the turbine blade would experience. We see that we get a slightly larger tangential velocity due to wake rotation. Now we have all the terms we need for the blade element momentum model. What remains is to find the optimal power coefficient. This upcoming part will require quite a lot of math from now on. Replace this Vt from the power and continue to look for an expression for A'. Combine. Replace V out using the actual induction factor. Expand the square. V in cancels. Remove minus. Place 4a outside parentheses. The two cancels. Divide by V in. Replace the expression with the local tip speed ratio. And divide by it. Expand the parentheses. And reorder the terms. We now have a traditional second order equation, which we know how to solve. As A' should be positive, the true solution should be with a plus sign. Let us rewrite the answer a bit. Multiply by 4 and place 1/2 outside the square root. 1/2 is the common factor. Let us save this one. Let's bring back the expression for the power. Yet again, replace Vt using the angular induction factor. Combine. Multiply and divide by V in order to match the expression for the local tip speed ratio. Use the continuity equation to replace the mass flow. Use the actual induction factor to replace Vt. Combine. And reorder. Now we want to rewrite it as a power coefficient. Replace the power. These cancel. Use the expression for the angular induction factor. One half cancels, and we have an expression for the power coefficient of the segment. Let us plot it. First, plot the Betz solution for optimal power coefficient as comparison. We will now plot the new expression for a large tip speed ratio, here 20. As we can see, they are almost identical at this tip speed ratio. Let the tip speed ratio decrease. When we have reached a tip speed ratio of 5, we can see a small difference between the two. Decrease the tip speed ratio to 1. Now we can start to see a notable decrease in power coefficient due to wake rotation. Let it go down to 0.1. Here the power coefficient is significantly lower. Let us also compare the optimal value for the axial induction factor. In the Betz theory it was 1/3. Now it is approximately 1/4. We update the limits to these new values. We will need them later. For the maximum power coefficient, all we can say is that it is below 16/27. To finish, let the tip speed ratio go down to 0. Let us find the optimal power coefficient for this segment. Same as for the Betz theory, we differentiate with respect to the axial induction factor. Use the product rule combined with the chain rule for the second term. Multiply by inner derivative. Two lambda squared cancels. Remove parentheses. 4/2 is 2. Multiply all terms with this square root. Remove parentheses. 2 times 1 minus ai over lambda squared is a common factor. Simplify the parentheses. Move the square root to the other side so we can take the square of both sides. Note that the left hand side is negative. Check the right hand side, as both sides should have the same sign to allow us to take the square. As a is smaller than 1/3, this factor is positive. A is larger than 1/4, so this factor is negative, which makes the whole term negative. Hence, we have the same sign and we can square them both. Expand the square. Subtract 1 from both sides. For 1 minus a over lambda squared cancels. Remove parentheses. Combine and solve for lambda squared. This equation will give us the optimal axial induction factor if we know the local tip speed ratio. We will leave it on this form for now. Let us calculate the corresponding optimal angular induction factor. Insert a recent equation for the axial induction factor. 1 minus a cancel. Write with a common denominator. Expand the square. Expand the parentheses. Collect the terms. Note that this expression is a square. The square root of a square is the absolute value. Use the limits for a to determine if they are positive or negative. As a is smaller than 1/3, the denominator is positive, the absolute value can be removed. A is larger than 1/4, hence this is negative. Change the sign. Write with a common denominator. Collect the terms and simplify. We now know the relationship between the optimal angular induction factor and the optimal axial induction factor. Let us plot it as a result of the local tip speed ratio. The dashed line is 1/3, so the best value. We see that at low tip speed ratio, the optimal axial induction factor is lower. We can also see that the angular induction factor is low for large tip speed ratios. When tip speed ratio goes to 0, the optimal angular induction factor diverges. When we see this divergence, note that the angular induction factor is defined with a division with the rotational speed, which goes to 0 when the tip speed ratio goes to 0. Hence, this divergence can be expected. In the final step, we are going to move from calculating everything from our segment and instead do the calculations for the full turbine. We get the power by calculating the sum over all the segments. Use the relationship between the power and the power coefficient for the segment. Insert the area for the segment. Assume that the segment width dr is small, which will turn the sum into an integral. Move constants outside integral. Replace the power with the expression for the power coefficient. Divide by 1/2 rho v cubed. Divide by the area. The turbine area is pi r squared. Cancel pi. Use the expression for the power coefficient of the segment. We note that the parenthesis is 2a prime. Combine these two. Replace a prime with the optimal value. Insert into the equation for the optimal power coefficient. 2 times 4 is 8. As it now is an integral, we can drop the subscript a for all terms. This is an integral where both a and lambda are functions of the radius. Start by making the substitution using the definition of the local tip speed ratio to combine lambda and r. Solve for r. We also need the derivative to do the substitution. Solve for dr. Now we can replace r. We can also replace dr. Finally, we need to update the limits. We can directly see that lambda r of 0 is 0. We can also see that lambda r of capital R is the tip speed ratio for a full turbine. Combine. Note that these are 1 over the tip speed ratio squared. Combine. Let's do another substitution to combine lambda and a. Start from the relationship between them. This is a cubic equation, but we do not need to solve it here. Calculate the derivative. Use the quotient rule for the derivative. Use the chain rule for the left-hand side. Start by differentiating the denominator. Differentiate the first factor, second constant. First factor constant, differentiate the second. With the inner derivative. Denominator constant. Nominator constant. Differentiate denominator. Divide by denominator squared. 1 minus 4a is a common factor. Expand this parenthesis. Expand this expression. Collect the terms. Both these are multiples of 3. 3 is now a common factor for the full expression. Expand these parentheses. Same for these. We can cancel for a. Collect the terms. Divide by 2. Multiply both parentheses by -1. We can now see that this expression is a square. Solve for d lambda r. Replace d lambda r with our expression. These will cancel. Eight times 3 is 24. Combine. Let's go back to the original equation for lambda. Use it to replace lambda squared. Combine these. Update the limits to complete the substitution. The lower limit can be calculated by setting lambda to 0. We can see that it's the second factor that is 0 in our valid interval. Hence, a of 0 is 1/4. We leave the upper limit as it is for now, which is solved by our equation for lambda. Let's make yet another substitution. This time, set x equals 1 minus 3a. Solve for a and calculate the derivative. For the upper limit, just insert the equation. For the lower limit, we can solve it. We see that it becomes 1/4. Replace with the expression for dA. Replace denominator. Replace the remaining a's. Update limits to complete substitution. (24/3 is 8. Make the denominator 3 everywhere. And place all 1/3's outside parentheses. 3 to the power of 6 is 729. Remove parentheses and collect the terms. Same operation for second factor. And for the third factor. Now we will expand all the squares. The aim is to expand the entire polynomial. The reason we are doing this is because we know how to integrate polynomials. We will continue and expand the remaining 3 factors. Start with the last one. Now we collect all the terms before the next multiplication. Finally, multiply the last 2 parentheses. and collect the terms. Divide all terms with x squared before we can integrate them. We can remove the minus sign by flipping the integration limits. Now, perform the integration. (76/2 is 38. 372/3 is 124. 288/4 is 72. This is our final expression for the maximum power coefficient with the wake rotation. A of lambda can be calculated with this equation. It's a cubic polynomial and will thereby have an analytical solution. While I will skip solving it here, one can show that the following expression will be a solution to our given interval. Combined, we can calculate the maximum power coefficient as a function of the tip speed ratio. Let's end the video by plotting the results. The dotted line is the best limit, 16/27. The black line is our new result for the maximum power coefficient. We can see that turbines that rotate fast will theoretically have a higher power coefficient. This new expression will still have almost the same limitations of the Betz theory. The only limitation that is removed is that the wake rotation is included. Hence, to reach this limit, we still need infinitely many infinitely thin blades to reach an even pressure drop that we have in the theory. For a real turbine, the finite number of blades and drag losses will make the performance lower than the maximum predicted here. With this, I will end this video. Thank you.